Happy Thursday, said Strat students. Today we're going to talk about geologic correlation, which effectively is being able to go to one stratigraphic section of rocks. So say you are in central Utah, and if you look over you're in Bryce Canyon National Park, say over here on the right side of the figure, and you see a sequence of stratigraphy that's made up of some aeolian sandstones and some fluvial sandstones and even some mudstones and shales, and maybe the top of the section is some marine shale, because that's what the sequence on the Colorado Plateau in central Utah looks like. And then you go about 100 miles south on your family's vacation to the Grand Canyon. That's down here. And you see another sequence of rocks. And at the very top of the Grand Canyon section, you see some aeolian sandstones and some fluvial sandstones, but then you see a whole sequence of limestones. And your questions is, are these sandstones that are right at the top of the Grand Canyon the same as the lower part of those rocks that you saw at Bryce Canyon? So essentially, the schematic image at the top here is the same as this image towards the bottom, where here's the Grand Canyon section. And in fact, many of the rocks that you see in Bryce Canyon in central Utah are the same as the rocks that you see at the Grand Canyon. And this lecture is about how do you determine whether or not those rocks actually correlate. Correlate is the idea that these are the same rocks. They covered the broad, vast, same area when they were being deposited. But how would you actually tell them that, say, this sandstone at the top of the Grand Canyon actually is similar to a sandstone you might find over in Frenchman Mountain? So our lab QB3 is going to be focused on correlating stratigraphy that you are identifying within the Chidam Basin. But again, if you're looking to the east, and again, this is similar to rocks you might find in the Grand Canyon. You might go out and you might find a layer of sandstone, which I'll color in blue, and then above that is the Bright Angel Shale, which is near the bottom of the Grand Canyon and is a very well-known shale. And then above that is the Mauve Limestone. So you go out to the lower part of the Grand Canyon, which are rocks from the Cambrian period, which are roughly 500 to 530 million years ago, and you see sandstone, shale, limestone. And you can see there's roughly a third of each within that stratigraphic section. Well, you move to the west and you find rocks of the same age. How do we know that? They've got similar types of fossils. But what you see over in the west is that there is a similar sandstone at the base, the Bright Angel Shale is right above the sandstone, and then we've got limestone. But notice the limestone in the eastern part of the section is much, much thicker than the limestone in the western part over here is much thicker than the limestone in the east. So the question is, what is the relationship of these rocks? And if you look closely, you can see that they are, let me use a different color, I'm going to use yellow, that they are related. There are some intertonguing relationships. But what this shows is that there are some lateral equivalent features here as well, where in the early Cambrian in the west, when you had limestone being deposited, that limestone graded offshore. Limestone comes in warm, shallow waters. Shale is typically formed in deeper marine waters. So we're going from shallower to deeper as we moved to the east back during the Cambrian. There were times when it was all shallow and warm. There were times when they were laterally graded from the limestone into the shale. And how this would look on a cross section, if you were to cut through the earth, is you would see these intertonguing lateral relationships at parts. That's why these correlations have these kinds of relationships. Years ago, where you see that in places there are lateral changes as you move from one depositional environment to another. So there are three main types of correlation. There is lithocorrelation, which is correlation based on rock type. There is biocorrelation, which is correlation based on fossil assemblages, where you're essentially correlating the environment of which it can be related to time as well. And there's chronocorrelation, which is based on time events, where you're not necessarily, again, correlating rock units, but you're correlating specific events. An example of this would be an ash bed. An ash bed will explode. And if you have a volcano that erupts an ash cloud, that ash cloud covers everything, all depositional environments. So you might find a particular ash that covers lake deposits and wind deposits and river deposits and even marine deposits. But you could correlate that ash bed and it represents a specific unit of time. Here, or two. So correlation is about determining how two sections actually compare. So here's section X and section Y, and you can see if you have shale, limestone, sandstone, shale, limestone, I don't know what we'll call the white unit. It doesn't matter what the units are, but what you notice, you have the same pattern, because here you have shale here, and there's a limestone above it. And the easiest thing to do would just be to draw contacts at those boundaries. And the assumption you would make is that the limestone in section Y is the same at the limestone at the same stratigraphic level in section X. And hopefully you would have some age information or some other information that might tell you that's probably right. But I'm going to make the point here that that doesn't have to be the case, because whenever you go out to set a stratigraphic section, you don't always know what the age is, and you don't know what level you're starting at. And let's say that that same section X, if you look over in section Y, what if you actually came on that section at a different stratigraphic level? There was either some erosion or there was some burial, and what you can see here is that there's shale, limestone, white. And then that's sandstone. And what this is showing is that here's shale, limestone, sandstone. How do we know that this contact here, the shale limestone, isn't the same as this contact here? Meaning that actually the correlation should look like this. Well, you might say there's no white unit, but it's possible that the white unit is in some sort of lateral relationship like we saw in the last. And so it's possible this white one actually pinched out laterally, and here we have the sandstones above those correlating in that mechanism. So how do you distinguish between those two? You need to look for other clues within the rocks and know something about the age of the stratigraphy. So you should be familiar with this figure. We did this in the Zoom lecture. If you haven't seen that, I think you should go back and take a look at it. But this is a pretty important idea on trying to understand how do these two correlate. Now, the first thing I look for is specific contacts. And you can see there's a limestone shale contact here, a limestone shale contact here, a limestone shale contact here, and a limestone shale contact here. So initially I might say, oh, well, maybe these limestone beds correlate and these limestone beds correlate. But we could do an alternative correlation in red, or say, well, maybe that's not true. It looks like that there's a change from, you could correlate this limestone shale contact with this one, which would mean that this must be off the figure. There might be limestone up here. We just don't know because we haven't measured that. But maybe this limestone correlates in that way. Or finally, there's a third way to correlate these. And in fact, that these limestone units, that we could think of these limestones as being atolls or little islands of limestone within a marine setting in a shale, which is what you might find, you find specific coral reefs. So we might think that these little limestones actually just form and I'm doing, this intertonguing relationship, and then the shale, and let me see if I can, I'm going to color in this whole area. I'm going to color the shale in red. Oh, let's color it in black. But you can see the shale is going to be everywhere else. And my point is that all of these are plausible relationships. So if we move on, you can see possible solutions to that slide. This was my correlation number 1. This was my correlation number 2. This was my correlation number 3. Or it's possible that even those could have correlated. And so you just need to be careful. You should aim for trying to what's the most plausible correlation. All of these are possible, but you just need more information than just the lithologies. You need to know something about their age to know which one of these correlations is correct. Sometimes you don't get to see the rocks at the surface of the Earth in outcrop form. I've given an example of the outcrops over here, what a correlation or a stratigraphic section you might have. Sometimes you just have data from wells. You're going to have data from wells next week in your lab, and what you're going to see is as you have a well, you're gonna find evaporites and sandstones in some wells. Other wells might have those sandstones at a slightly different depth, and you're going to need to figure out how do these actually correlate. And what you can see here is there's a sandstone bed that correlates from the far eastern side. It correlates through 2 wells, and then it looks like it pinches out because at that same stratigraphic level, you don't get any of that sandstone. So this must be some sort of sand sheet or delta that moves across the basin and pinches out at this location. Here's a little sand lens, maybe related to some sort of fluvial channel. I'm not sure, but it's a lens that really only shows up within that sheet. This is what a lot of petroleum geologists look for. They look for these sand lenses that might be reservoirs for gas, and the gas may be coming from source rocks in the shale surrounding it. And you can see at the top of this section, you have anhydrite, again, evaporites. Those evaporites are thickest off to the east, thinner out here, and there's more limestone off to the west. That's what these little humped areas are limestone. So this is some sort of probably marine basin or potentially lake basin that appears to be changing in thickness from one side to the other. But you can see the correlation is non-trivial because there are areas that have little lenses that pinch out, others where you can follow them and they continue. This is the last figure in chapter 12, and it just shows that you can use lithologies. You can also use these changes in different properties of the rock, such as density, that you can get using little sonar techniques within the holes, or using actually gamma ray techniques where they actually bombard the rocks in these core holes with X-rays, and depending on how the X-rays penetrate through the rock, it tells you something of the density, and use those density changes that show up as these little wiggles to correlate through the section, where you get gamma ray changes and sound changes, how does sound travel through those rocks that help you interpret the lithologies. In addition to using the actual rock type to correlate, we can correlate based on fossil assemblage. Here you can see the same fossil assemblage at the base of this rock. These correlate. They don't need to be in the same rock type, but this indicates these formed at the same time. Also, we have a correlation here where these correlate based on fossil assemblage. And what this shows is that you must have some sort of unconformity or a disconformity. It's an unconformity. It's a special kind of unconformity called a disconformity. They're parallel layers. But you had a hiatus in deposition, or you had erosion that removed a whole package of rocks. The only way we know that is through the fossil assemblage in this biocorrelation. And the last kind of correlation that I had discussed are chronocorrelation. This can be thought of in sort of two ways. One is event correlation. What are events? Well, I described, how an ash layer, or sometimes you might correlate unconformities within a section. That would be correlating usually a time of erosion. And finally, an event correlation would be extinctions. The geologic time scale is based on biocorrelation and where there's big extinction events. The major periods and eras are all times and epochs are defined by mass extinctions that have been correlated around the world, but that's a specific time period, which is why it makes such a good geologic time scale. And then transgression, regression in just a moment. I just want to do a couple examples of what does this event stratigraphy mean. Well, you get two sections, one in the west, one in the east. You can see they both have shale at the top. They both have sort of Aeolian sandstone at the bottom, but they're a little bit different. Here are some swamp deposits that don't show up over here. There do seem to be sandstone and shale in the middle. So what you should always start with when you do a correlation is correlate the unconformities. Now here's an unconformity that extends somewhere off here, but we don't know where it goes. So we know it, lines don't just end. There are no faults in this section. That's at least an a priori assumption. There could be a fault, but we don't know that. And we're assuming for this study that that's not the case. So how would I do this? Well, we need to think about so the reason I've brought this up is you can correlate unconformities, and I won't dwell on this specific correlation, but hopefully you could take a look at this, and I may give you an exercise that's similar to this to work on as well, to see if you can continue this correlation, because I would correlate those sandstones. I would correlate the shale and sandstone over to here, and then it gets a little bit tricky because I'm going to just complete this for you. And what you can see is I have correlated the sandstone, saying this is the same sandstone over here, and it's the same sandstone as that. So what this shows is this is beach dunes, that then if you're on beach dunes, then you go to beach foreshore, which are these, and then you get to offshore sandstone. So here we're going from deeper water to shallower water, and over time you can see if we were there, we would have beach, or we would have dune, beach, shallow water, and then eventually deep water. And so we're going offshore in this direction, and this is how that would look like in a correlation. But another kind of event would be a marine transgression regression. What you should see here is that the units that show up in the section on the right are very different than the units that show up on the section on the left. So how do we correlate these two? You have to make some guesses of what's happening in the middle. But what we can see is that these rocks are going from shale, which typically means deep water, to siltstone, which means medium, or not deep, not shallow, some sort of tweener depth, and then sandstone, which is shallow. So deep to shallow, and then we go shallow back to deep. So what's happening here is we look like we have a shallowing event in the lower part, and then a deepening event. Well, when we have a shallowing event, what does that mean? It means that sea level is falling. That is a marine regression. We've got a regression at the bottom here. And then when water's getting deeper, it means that the shoreline is moving inland. We have transgression. We have a deepening, and that boundary must be right in the middle at the shallowest point, which would be in the middle of that. If we go to the right-hand scale, we can see the same thing. We've got deepening going from sandstone to shale. And if we look closely, you can see that this lower part actually is shallowing as well, where we go from deep to marine siltstone, so we're getting shallower, to littoral sandstone, and then foreshore sandstone. So we're getting shallower here, and finally beach sandstone. So we're actually dry. So we're going from very wet to very dry. Again, a shallowing section, which is a regression, which ends right at this unconformity. You get above the beach sandstone, then you start having erosion because these rivers and wind are eroding the area. So in this case, we could and should correlate the events where we correlate the boundary of this regression, transgression that is going to occur right at that point. So that is a period in time when global sea level changed. We're not correlating stratigraphy in those parts, we're correlating the events. So I'm going to leave you with this last correlation. And you should be able to you should practice with these. Now here you can see Unit 1, the boundary between Unit 1 and Unit 2, and Unit 2 and Unit 3 correlate. And the boundaries between Unit 5 and Unit 6 correlate, but we're having an issue here because we have Unit 7 thrown in between 3 and 5. So what happens in this location? Well, my guess would be that Unit 4 and 7 are lateral equivalents and look something like that, where for some reason you've got a change in depositional environment from, say, alluvial fan to lacustrine. And above we have maybe playa that covers the whole basin, but you have a period of time where this depositional setting has lateral variability that might appear something like this. So here are a few options. Again, you might have some sort of one environment moving. If 4 is moving out over 7, it's going to look like example 1. If 7 is moving out over number 4, it's 2, or maybe they're equivalents and there's just intertonguing between the two of them. So thanks for bearing with me. Ultimately, the point of doing these correlations is being able to correlate between a number of different sections, one here, one here, one here, that if you can correlate between spatially separate sections, not just within one cross-section, but within multiple, then you can start to pull together what's called a fence diagram, a three-dimensional correlation figure that shows how some sandstones are going to pinch out towards the northwest in this case, and what the three-dimensional geometry, it looks like it's much shallower water off to the northwest. It looks like it's deeper, there's more sandstones off to the south and east. And that's the ultimate goal, is to be able to fully interpret the three-dimensional changes within that basin. So thanks a lot. Hopefully you've got a good summary of Chapter 12, and I will see you soon.